All right, so let me kill my video and start sharing my screen and we'll get going. Um, okay, so yesterday we went through, let me get the, sorry, hold on just 1 second. It's hiding the chat from me for some reason. Let me see, I just got a question from Emily asking if I'm gonna post my notes, and yes, they're up on my group's website, so if you want a copy of the notes, so at the end of yesterday's lecture, I just printed this OneNote page to PDF, and it's up on my group's website. Thank you, Chris, for posting the link. All right, so yesterday we talked, it was all math stuff, and today we'll start taking everything that we talked about yesterday with functional integration and all that fun stuff and start applying it to StatMech problems. And my goal for today is basically to get through the what we call the particle to field transformation, and basically have some discussion of maybe of the structure of a field theory, and then we will get into some working out some example systems probably next time. I don't know that we'll be able to get through many more detailed examples and demonstrations of the application today, but today's goal is really to get through the structure of the field theory. All right, so let me see. So some good references for this. Sorry, trying to get my other screen up. Sorry, I know I feel really disorganized here. So some good references for this first part that I'm going to talk about is the early stuff in chapter 3 of Hansen and McDonald. Hansen and McDonald, where they have a nice discussion of how simple particles interact with fields. This book is Theory of Simple Liquids. Simple liquids. But of course, most of the meat of what I'm going to talk about comes from section 4.1 in the book by Glenn Fredrickson, the equilibrium theory of inhomogeneous polymers. Right, so section 4.1 of equilibrium theory of inhomogeneous polymers. And this is the thing by Glenn Fredrickson. I really recommend this book a lot. It really lays out the material very well. I have my like 10-year-old copy that's just taped together and yellowing pages and falling apart. It's one of the few books I went back to my office to get when we went into the shutdown for the coronavirus. All right, so I guess from the top, I want to make sure that I emphasize one thing, one point very clearly, and that's the theory that we're going to develop. It's primarily going to be for a coarse grain or a mesoscale approach to modeling materials. It's you're generally not going to obtain things like like a liquid-like structure like you would be able to capture in a G of R or from a liquid state theory. Though recently our group has shown that it is possible, but in most applications, you're not going to be doing this. And so you really shouldn't think of this as being like something where we're going to resolve things all the way down to the atomic scale. And that's not really the goal of this. And so the way that we're going to start off is we're going to kind of gradually build up in complexity. And so the first thing we're going to do is just consider the case where we have a single particle that's interacting with some fixed and constant external field. All right, so we're going to consider one particle. So I'm going to use little n for the number of molecules that we have. And so little n equals 1 in a fixed external field. And I'm being a little bit vague about what this field is. You can think about it as, one of the examples that we will go through is when this is the electrostatic potential. And you can just basically evaluate the energy of that particle just by evaluating the field at the particle's location. And for the sake of this discussion, we're going to generalize beyond that. And so the way that we will write down the density of this particle, so I will use a row with a hat on it to indicate that this is a particle density, and it's just going to be a delta function. All right, so it's just at some location in space. All right, so the particle occupies at some position in space, r sub I, and the subscript I on the particle coordinate indicates that it's one of the particle positions. And I will try to switch to using J for this so that we don't get confused with the imaginary unit. All right, our external field is going to be W of R. Let me use lowercase w of R. Right, and so it's just some spatially varying thing that we're not going to specify. And so our total Hamiltonian of our system is going to be, right, so the Hamiltonian, or the total energy of our system, there will be, the usual kinetic term, so 1/2 mv squared. There's, in general, there could be a potential energy term, and then there will be the interactions of the particle with this external field, right? And W is the thing that we're going to care about for now. I'm curious how much y'all can hear my kids yelling in the background. But anyway, the total external potential is going to be, or the interactions with the field are going to be given in this form, right? So it's just rho hat times the field W. And of course, if we plug in for rho hat, it's just a delta function. And so then this would just be from the properties of the delta function, right? We would have rho r minus rj, W of r. And so this is just the field evaluated at the position of the particle. Simple enough. And then, we're going to be building up a stat mech theory. So we're going to be very interested in writing down the partition function of this system. So again, for this simple one particle system, we write down the total partition function of the system. This would be, in general, 1 over n factorial, integrate over the momentum of our particle, integrate over the positions of our particle, then e to the minus beta h. And of course, we know that standard StatMech practice is that we can integrate out the kinetic energy term and get the thermal de Broglie wavelength. So that always goes away. So we'll have 1 over n factorial lambda t cubed. And I realize it's, in this n equals 1 case, it's useless for me to carry around the n factorial. It's just another factor of 1, but I'm just carrying it to be explicit. And then we have this this field term, e to the minus beta w. And I'm going to make a change of notation because this is where it happens in the notes that I'm reading from. And so going forward, I'm going to assume that all energies are going to be in units of kT, right? So so in other words, I'm going to set beta equal to 1, right? So our betas are just going to go away. And so this thing just becomes 1 over n factorial lambda t integral dp j integral dr j. Oh, sorry, we got rid of the momentum term. Then e, clean this up, integral drj e to the minus w of rj. All right, and so this thing is going to be what we use to define our single particle partition function, right? And so it's basically the configurational integral of a single molecule in this simple system in an external field. And so we're going to define a thing, Q, that has a functional dependence on the field W. And we're going to define this thing as 1 over V integral over the volume of our box, drj e to the minus w of rj. All right, and so then we can plug that guy. So we use that and plug in here so that we get z equals, what do we have? V over n factorial lambda t cubed, and then q of w. Easy enough. All right, so all we've done is just simply made up this external potential field and now and written down what a partition function would be for a really trivial system in that case. All right, but what happens when we go to a system with many particles? Well, the first thing that changes is that we have to deal with an interaction potential. And our density gets a little bit more complicated. So if we have for many particles, right, we're going to have a case where, and of course, Z has its standard definition, so it'll be 1 over n factorial, lambda t to the 3n now. And again, lambda t is the thermal de Broglie wavelength. Then we have this horrible thing that's at the heart of just about all of StatMech, where we have to integrate over the positions of all of the particles and evaluate the Boltzmann weight, right? So it's going to be e to the minus u of r to the n. And again, I'm not writing out the beta. I'm assuming that it's gone from the equation. And if we have a system that interacts with pairwise with a pair potential, right? So if we only have to deal with pair potentials, then we can write this potential energy, u of r to the n. I'm going to write it as 1/2 1 to n, sum j equals 1 to n, and j not equal to I, right? So we skip the self-interaction here. And then we have some pair potential, and I'm trying to write this, emphasize that this is a lowercase u of ri minus rj. Right, standard definition of the pair potential, and we have the prefactor of 1/2 out front because we're taking both sums from 1 to n. All right, and then the microscopic density, right? So the rho hat for this system that now has n particles in it is now going to be a sum of delta functions. So we can define the microscopic density rho hat of r. Right, this is now going to be a sum over all particles, j equals 1 to n, delta of r minus rj. Right, and so again, instead of it just being a single delta function, it's now a sum of delta functions. And the thing that we want to do as the next step is rewrite our potential energy function in terms of this rho hat. And there's a couple of things to point out about that, right? So we can write it as rho of r to the n. This is going to be, so we're trying to get this into an integral form. So this will be integral dr prime rho hat of r u of r minus r prime then rho hat of r prime. And then there's a problem here though, because with the way that we've written this term, we've included the self-interaction, right? There's no way in this this integral form to preclude the I equals j term. So we have to also subtract off the term that contributes from the self-interaction, right? There are going to be little n terms where we have to evaluate u of 0. Right? And so this already kind of gets at one of the kind of challenges that's going to show up and rear its head in this particle to field transformation, because we need this u of 0 to be finite. Otherwise, we're going to have these competing infinities, because we'll be evaluating an infinity here anytime we have a self-interaction, and we would be trying to subtract that off, and that's just not the most well-defined mathematical operation. And so that's why we have to subtract off this minus 1/2 n u0. And so generally, not always, we will see cases where it's possible to get around this, but generally we want u of r to be finite at r equals 0. And so that's going to be one of the things that we need to keep in mind. So, all right. So then I'm going to start collecting some of the, we're going to end up in our partition function with a bunch of stuff that starts building up in the prefactor. And so we see that we're going to have an exponential that has this minus 1/2 n u of 0. Actually, let me just write this out. So we have 1 over n factorial lambda t 3n integral dr to the n. And then we have e to the minus potential energy. And so we end up with two exponentials. So e to the plus 1/2 n u of 0, and then times e to the minus 1/2 integral dr prime, rho at r, u of r prime, rho at r prime. And these should have hats on them because they have the particle densities. And I'm using a notation here, just again to clarify this, that rho hat r is just rho hat of r. I'm just using a suppressed notation to condense things a little bit. This term is a constant, right? It doesn't depend on the particle coordinates, so we can pull it through the integral and just lump it into the a prefactor, and we have this lambda t raised to the n, and we have an exponential raised to the n. So I'm going to define something just to collect some of these constants. So I'm going to say that z0 is 1/2 u0 over lambda t cubed. And so then we have a partition function that's z0 to the n over n factorial. And then we have this exponential term, right? So integral dr to the n, e to the minus 1/2, dr prime, rho of r, u of r prime, rho of r prime. Okay. Now, hopefully, this equation, this thing is starting to look a little bit like the some of the Gaussian integrals that we talked about at the very end of the lecture last time. And so this is where we're going to start. We're going to transform this problem and work towards getting this kind of horrible n squared operation out of our partition function. And we're going to get the particle coordinates out of our partition function and replace them with chemical potential fields. And I want to say here that, there's actually multiple ways of deriving a field theory. I'm only going to show one of them. That's generally known as the Hubbard-Stratanovich transformation. It's the one that, well, apart from being the one that I'm most familiar with, it's also one of the more common ones. But it does have its own limitations that we'll talk about as we go through it. So let's get into the Hubbard-Stratanovich transformation. Stratanovich. And so we're going to assume something. We're going to assume that we're working with a case where u of r, our pair potential, has a functional inverse, right? So we're going to assume that u of r so there will be something that we're postulating exists, this u of r, or u inverse of r. And if this is true, then we can use those Gaussian functional integrals from last time, right? So if that's the case, then we can say that the exponential minus 1/2 integral dr prime, rho of r, u of r minus r prime, rho of r. These all get hats on them because they are have the microscopic densities in them. We can say that this is equal to, right, so the equations are big, so I'm going to give myself some space here. Integral over some chemical potential field dw, exponential of minus 1/2, again double integral, dr prime, w of r, sorry, u inverse of r prime, w of r prime. All right, so we have this term from our Gaussian functional integrals from last time, and then because we have the minus sign as the prefactor in the thing that we started with, we pick up a plus I integral dr w of r. And again, in the version that we did last time, these were, I forget if they were j or f of x, but it was one of those two. And so then the rho hat goes into that location in the equation, and we get rho hat of r. Right? And then this is all divided by this normalization constant, which is, again, I'm going to cheat and just copy things. right? So it's divided by this thing, and we're going to define this thing that's in the denominator. We're just going to give it a label of omega naught because it's just going to be a constant that we lump into these prefactors that we're building up, and we're just going to forget about it. Right, so we're going to define this denominator as omega naught. And so then we're going to just leave that thing alone for a while. You can actually analytically calculate it, but it's usually something that you would do after you've discretized the theory that you're working with. All right, so let me see. So the next thing that we do is take this, and we're going to replace the exponential that we had in the partition function with the right-hand side of this equation. All right, so we're going to scroll back up to our partition function here, and we're going to get rid of this exponential, and we're going to replace it with the right-hand side, where we have this horrible mess of constants over there, but we'll clean things up as we go. All right, so we're going to plug this into z. All right, so we have our partition function z. Let me see. So we have an omega naught that we have to keep around. We have our z0 to the n from the prefactor. We still have our n factorial, omega 0. Now we have a functional integral over this field that we've introduced, and we still have our particle coordinates. Right, so things are kind of a hot mess for the moment. And then we have the exponential of -1/2 integral dr prime. We have w of r, u inverse w of r prime. So w of r prime. Right, and then I'm going to multiply this by an exponential. Right, so we have an exponential of everything that's in the brackets up here at the top. And so there's a sum of two terms. And for the moment, I'm going to make that a product of two different exponentials. Right, so then this will be times e to the plus I integral dr w of r rho hat of r. Right, and of course, all of this is inside the integral, right? So it's all being operated on by the integral. I'm going to put a star by this equation because we're going to come back to it later on as one of these intermediate steps, because it will just have some utility for us. But for now, ignore the star. We'll come back to it later. All right. So now the thing that we can do is focus on all of the terms that involve the particle coordinates. Right. So we have particle coordinates that show up in the integral over the coordinates and in this second exponential. Right, so we're just going to focus on those. And so we can just collect them together, right? Because this exponential will commute with this integral operation. So we can just pull that through the integral because it doesn't depend on the particle coordinates. And so then we have integral dr to the n e exponential of I integral dr w of r rho hat of r. Right, so this is the thing that has all of our particle coordinates in it. And now we can write out rho hat in terms of the delta functions. And so this is equal to integral dr to the n e I. And so if we write out this thing as delta functions, we'll have sum over j integral dr w of r delta of r minus r j. Right? And now we can evaluate this integral for all of them. Right? And the delta function is just going to return the field at particle position rj. So we have integral dr to the n e to the I sum over j w of r j. And since we have a sum inside of the exponential, we can also rewrite that as a product of exponentials. Right? So then this is equal to dr to the n e to the I w of r1 times e to the I w of r2, and on and on and on. e to the I w of r n, right? The last coordinate. And now for each one of these, we have a single integral that we can associate with it. And so we can collect all of them and isolate them. And what we end up with is basically integral er dr1 e to the I w of r1 integral dr2 e to the I w of r2 on and on and on, integral drn e to the I w of rn. And so we have little n of the same thing multiplied together over and over and over again. And so we can basically just call this, we can just rewrite this as integral dr e to the I w of r to the n. Right? And when we started off today, we defined the partition function for a single particle interacting with the field. Right? And so we can use that definition again. Right? So as we come down, we're going to use that q of w we defined as 1 over v integral dr e to the minus w of r. And the only thing that's really different here is that instead of I seem to have lost a minus sign. No, it doesn't matter. The only thing that's different is that now we have an IW of R as our potential field, right? So we have integral dr to the n e to the sorry, let me see. So we have to multiply and divide by v to use this definition of q, and so we'll have v q of IW to the n, right? And then the last simplification that we're going to make, so this becomes v to the n, which is going to go in our prefactor, and then q to the n, which again, functional of IW. And then the last thing that we're going to do is write this q in the exponential so that we can group it with the other terms that involve w that are also in an exponential in our partition function, right? So we want to write it as an exponential. And so the thing that we use is, again, x to the y. You can rewrite this as the exponential of y times the log of x. And I always write out natural logs as log. So this is a natural log. It's not a base 10 log, even though I write out the log. So this whole thing, this whole term becomes v to the n e to the n log q. All right. And so now we can collect everything by plugging this back into our partition function. And we will have, let me see. All right, so we're going to plug that back into our partition function, and we get z0 to the n, v to the n, for n factorial, omega 0. Yeah, so our prefactor is getting a little hairy. Functional integral over the field configurations, and then e to the minus h of w. And we'll talk about this thing a little bit. So then h of w is going to be 1/2 integral dr prime w of r u minus 1 of r minus r prime w of r prime, then minus n log the natural log of q of IW. All right, and q of IW is, I missed the sign somewhere, but it's defined as e to the minus I w of r. All right, so let's talk a little bit about what we've done, because this is kind of the first big result of this particle to field transformation. The kind of spectacular thing, at least to me, that we've done is that we've taken this this problem where we formally have to evaluate the interactions of all the particles with all of the other particles, and we've gotten the basically we've gotten the particle positions out of the out of the equation, right? Our partition function doesn't have an explicit dependence on the particles anymore. We've kind of obfuscated everything into this weird chemical potential field space, but it's still, we've gotten rid of a lot of the hairiest parts of the central problem of statistical mechanics, right? And that's, evaluating these Boltzmann weights. And so we can talk a little bit about the structure of this of the resulting theory. And part of what we're going to spend the latter half of today talking about is how we can derive operators for it. But the thing that's convenient about it is that now our Hamiltonian and our partition function has an explicit dependence on this field W that is continuous and differentiable, right? So this is now something that we can differentiate, unlike rho hat, which is has all these delta functions and is kind of a poorly behaved field. This W of R is now a continuous thing that we can work with. Of course, the big wrinkle that we have is that we've introduced this imaginary unit, right? And that's very problematic because H of W is in general complex now. And if we're thinking about using something like Monte Carlo sampling to numerically to numerically attack this theory, then that's not going to work, because that means that e to the minus h is not positive definite. It can be negative, it can be complex valued. And so standard Metropolis Monte Carlo is just out of the game, right? You have to do something different if you want to sample this partition function. But as we will see over the coming few lectures, the thing that's nice about it is that this H, actually I didn't give the name for it, so this thing is referred to as an effective Hamiltonian. And the effective part on that is very important because it's not a real Hamiltonian. You can't get equations of motion out of it. So it's we call it an effective Hamiltonian because it plays the role of weighting the microstates of the field theory, but it doesn't have any sort of like true, total conserved energy character associated with it. The cool thing about it, though, is that it does have something of a free energy character to it. So like this n log q term, what we're going to see is that this is actually related to the excess chemical potential of the system. And so the chemical potential is like a partial molar free energy. And so there is a kind of free energy character to this effective Hamiltonian, and that's what makes it kind of useful to analyze analytically. And of course, the prefactor still has the entropy of mixing term, and this this n log q term basically tells you it gives the contribution to the effective Hamiltonian that comes from basically the changes in the translational entropy of the particles or of the molecules due to the presence of this field, and it has the interactions with the field. And then this other term tells you about how the field is kind of modulated by the interaction potential. I mean, it's in this weird form where we have this inverse potential, but it's still it's informing how the fields are modulated by each other. And so it does have some free energy character, but there's also an entropy associated with the field fluctuations, right? So again, this path integral is saying that we have to integrate over all possible forms of the field W. And so there is an entropy associated with that can also be important. And in a lot of systems, that's makes a very important and like qualitatively different contribution to the structure of the theory. All right, so let me see. I guess before I go on, I mean, there's a couple of things that I want to talk about today. First is some of the types of potentials that you can do this with. So what are the sort of standard forms of U of R that we can work with? And then we'll talk about the operators for calculating different properties. But this is a good time to ask questions and have discussion if anybody is interested. If not, I'll just, I guess, carry on then.
Rob, can I ask you a question?
Yeah, of course.
So this U inverse of R minus R prime, how do I think about that?
What do you mean?
I mean, I can see formally what it means, but
So,
is it mapping a potential? Is it mapping distance now, or
I'm sorry.
so U is a potential between two particles that are in R prime, right? But
Yeah.
what does U inverse mean? Does that mean that given a form for a potential, it tells you the distance separation? Is that how I should think about that?
Um. Let me, not exactly. Well,
So, oh, sorry.
that's no. Go ahead. Go ahead.
So I think you have to think of U in terms of that whole term, right? This W U inverse W term.
Mhm.
So it's kind of like it's a coupling, telling you about the interactions of the particles at those 2 points, right?
Yeah, I see. So you have a chemical potential field at R and one at R prime, and you're talking about how they're coupling through U inverse.
I think so. I don't know if anybody has.
Yeah. I mean, that's yeah, that's basically how to think of it, I think. And I mean, the example that I think is the most intuitive will be when we apply this to Coulomb's law. Like that's one of the potentials where you can go through this that we'll talk about in a second. And the U inverse ends up being something like 1/4 pi grad squared. So then you end up with field grad squared field
Mm-hmm.
in that term.
Okay.
And so it's starting to look like Poisson's equation, right?
Got it. All right. Thanks.
All right, so let's talk through a couple of the potentials that we like to work with. So by far the most common one that people work with is just a very simple delta function repulsion, right? So if you just insert an energy penalty for having two molecules sitting on top of each other. You know, the Flory-Huggins potential with chi, that's usually that's often how that's how we will write that down for a field theory. Or equivalently, you can give this delta function a finite width and make it a Gaussian interaction potential, which is something that we've been doing a lot more recently in the field theory community, because it actually gets rid of a lot of the problems that show up in sampling the fluctuating field theories. And of course, we saw last time that Gaussians have a trivial Fourier transform, so then their functional inverse is very well defined. And because for a delta function interaction, the functional inverse of the delta function is just another delta function, right? Because again, if you think about this in Fourier space, we just when we Fourier transform the delta function, we just get a constant, and so then it's just 1 over the constant to get the inverse, right? So U minus 1 of R is just 1 over U naught then delta of R. Another very useful one is the Yukawa or the Debye-Huckel potential, right? So the Yukawa potential. Right, so this is U naught, so it has some energy scale, 4 pi R, then e to the minus a length scale, and then the separation. And typically this prefactor is going to be qi qj over epsilon naught, and maybe a relative dielectric. And of course, as kappa goes to 0, this is going to recover Coulomb's law. But this form you can actually get the Fourier transform of analytically, and so U hat of k here is U naught over 2 pi cubed 1 over k squared plus kappa squared. And so then U inverse is just 1 over all of this, right? So U inverse in k space I realize I'm not doing the best job distinguishing my k's from my kappas, but this k, that's a k, that one's kappa, that one's kappa, and that one's kappa. right? So this gives us our U inverse in the Fourier domain. And then if we take the limit where as kappa goes to 0 from the positive side, we can get the functional inverse of Coulomb's law. I guess I'll just to make this explicit, we know that this k squared, when we go back to real space, this is going to turn into something like a grad squared operator, right? So then we take the limit as kappa goes to 0 from the plot is. All right, so then we would have u of r, it would be u0 over magnitude of r minus r prime. Wait. Sorry, let me fix the left-hand side here. And in this case, u inverse of r minus r prime is going to be minus 1 by 4 pi grad squared, and then delta of r minus r prime. All right, so it's a kind of cryptic looking operator, I grant you that, but we'll see. We will work through an example with Coulomb's law next time to show how all of this works out. And so one of the things that's kind of important to note here is that, for any of the types of potentials that we use here, we need something that's going to be well behaved in Fourier space. And so something like the full Lennard-Jones potential is not going to work. You could probably work with like the attractive part of it. The attractive WCA potential, I'm sure, would be fine. But like, trying to do something like this for the full Lennard-Jones is going to be really problematic. All right. Okay, so that's it for types of interactions. And now the last thing that I wanted to cover, make sure to cover today, was how we go about actually calculating properties. And again, this is where field theory gets to be a little bit on the unusual side for most molecular modeling approaches. But generally speaking, the way that we're going to do this is going to be to derive operators that give us the information that we want once we take an ensemble average, right? So an average quantity is going to be defined in kind of the standard way. Right, so we have the average quantities in a field theory. Right, so if we want to calculate the average of something m, some quantity m, we need to write it as we need to be able to derive m as some functional dependence on w, because that's now our independent variable, and this is the thing that we need to evaluate, right? And then, of course, we normalize. And normally the way that we're going to go about deriving our operators is going to be to go all the way back to like classical thermo and the definitions that we work with there, and just explicitly take the derivatives. So we've been doing everything in the canonical ensemble, and so we go back to the Helmholtz potential, and we know that in this case we can write the chemical potential is going to be, for example, the F, the N, at fixed V and T. And we can plug in, minus KT, d log Z, dN, fixed V and T, just using the relationship from basics of StatMech. And then we can, start taking derivatives, right? And so we can explicitly differentiate with respect to N and get expressions for the chemical potential operator that might require us to average over fields. And we'll work through that one momentarily. Things like the pressure operator, we don't have pairwise forces anymore, but we can still derive an operator from d log Z dV at fixed T and N, and equations for the potential, or for the the potential energy. It's still KT squared d log Z dt at fixed N and V. And again, for this one especially, you would have to remember, where all the energy scales are that we set equal to, where we set the temperature equal to 1, and make sure to hit those with the appropriate derivative. But still, it's something that you can plug in and do. So let's go through this for the example of the chemical potential. So right, so for the chemical potential, right, so we have mu is going to be minus kT d log z dn. And if we scroll all the way back up to our n, we see that we have an annoying number of places where n shows up. It's all over the place in the prefactor. And then it also shows up as an explicit parameter in the Hamiltonian. And so we will have to take the derivative of the Hamiltonian with respect to n, and we have to get all the terms from the prefactor. So of course the prefactor is just in the end going to give us all the ideal gas contributions. It's not going to be all that exciting, so I'm just going to skip a lot of the calculus for that. So let me see. Actually, let me write out all the terms just so that we can see it. So we're taking the log of the partition function, and all those prefactors have like v raised to the n. And so when we take the log of v to the n, that's going to bring down n as a prefactor. So we'll have d by dn of n log z0 plus n log v minus log n factorial minus log omega naught, and then plus log of functional integral over the fields e to the minus w. Right? And all of this is inside the derivative that we're taking. So we start taking our derivative. We end up with the first term that's just kT log of rho over z0. So I'm just collecting all the first terms. Of course, we use Stirling's approximation to kill off n factorial. I'm just not showing it. And then we have, so we're taking the derivative of the thing inside the log. So we'll get 1 over the thing. And we already have a minus sign. So we have minus. In the denominator, we have the thing minus hw of omega. Then we take the derivative of the thing inside the log. And so d by dn doesn't care about the integral over the field, so it goes through there. And then we'll have integral dw. The derivative of the exponential, well, we're still going to have the exponential carried around, of course. And then we have minus dh dn, right? And so the minus sign is going to make this one a plus. So in the end, we end up with a plus dh dn that comes in here. And so then the operator that we need for our chemical potential is going to be kT log rho by z naught, right? Our ideal terms plus kT, and then the ensemble average of whatever this thing is, right? dH dn. Right, so this just looks like an ensemble average, and so this is now the thing that we need to take an average of to get our excess chemical potential. But of course, that's easy, right? The only place where n shows up is, if we go back all the way up to our Hamiltonian, is just as the thing multiplying log q, right? And so then this minus log q is really giving us the excess chemical potential. So we have that dH dn is just minus log of q of iw. Right? And so then our total operator for the chemical potential is going to be kT log rho over z naught and minus kT ensemble average of log q. And so this is, again, one of the really nice results that we get from a field theory is that the chemical potential is actually something that's very easily accessible, right? Like calculating this Q is kind of at the heart of doing a field theory. But once you calculate it, you have access to an operator that just straight up gives you the chemical potential, which is something that's often very, very difficult to calculate in a molecular simulation, and I'm using like molecular dynamics or something like that. All right, and what else? The other important operator that we need is the one for the local density, right? So if we want to calculate like a spatially varying density, how do we get that? So the thing that we're going to be after is something where we want like an average rho of R, right? So we have You know, maybe on average, we have some spatially varying density. You know, field theory is commonly applied to block copolymers. You know, of course, the different domains of a block copolymer would be spatially varying, right? That's a very common situation. And this is where we're going to play some tricks to get the operator that we need to do this calculation. So we're going to go back to the equation that I start above. So where we were at this intermediate step where we still had all the particle coordinates in the equation, but we also had introduced the fields. And so I am again going to cheat and just copy this whole beast. Bring it down here so that I can have it. Right. And the thing that we're going to do to get to our field theory density operator is going to be to write down an operator in this form of the partition function for the average density. And then we'll finish the particle to field transformation and see that we can get to the thing that we want. Right. So if we write at this stage in the particle to field transformation, if we write average rho hat of R, this is equal to Z0 to the N factorial lambda T to the 3N integral dW dr to the N, right? We would have our microscopic density. Then we have e to the minus 1/2 integral dr prime, W of R, U of R prime, using my shorthand from before. And then this at this stage, we still had e to the minus dr W of R rho hat of R. And all of this is divided by the big partition function Z. Right? This is just from the definition of an ensemble average. And the thing that we can notice here is that we can write this, we can get this rho hat as a thing to come into existence by taking, if we didn't have it here, we could get it by taking the derivative of this term, this exponential, with respect to I times W of R. Right? So we could take a functional derivative of this term, and that would pull down the rho hat and kill off the IWR for us. And so that's going to be the trick that we use to get our density operator. Right, so we're going to say this is equal to, right, so Z0 to the N factorial, lambda T to the 3N, and then over the big partition function, just to get it out of the way, integral dW e to the minus 1/2 integral dr prime, W of R, U of R prime, W of R prime. And then the thing that we're going to do is rewrite this rho hat times the exponential, right? So those are the two things that I haven't written down yet. We can say that this is now times minus the variation of everything to the right with respect to IW of R, integral dr to the N e to the minus I integral dr W of R rho hat of R, right? And all of this is still, you know, under the functional integral, right? So everything is still being integrated over the fields W. Right, and so this is a case where if we took this variational derivative, the variation with respect to I times W of R, the way that that would work out is that we would, you know, we'd taking the derivative of an exponential, so it's the exponential survives, but then we bring down the argument of the exponential and then take its derivative, and we have minus IW, so that would just kill off the minus IW. The variational derivative kills off the integral, and we're just left with rho hat. And so this gives us something that we can now operate on to get our density operator. And this thing, right, all of this whole term here, let me use a different color. This is the thing from above when we were doing the particle to field transformation that we showed was equal to e to the n log q. All right. So let me see. So this whole thing was then, yeah, so all of these integrals, this whole thing just becomes equal to e to the exponential n log q. of IW. Right? And so the thing that we get back at the end, so we still have our horrible prefactor, t0 to the n over n factorial lambda t3 n, and then all of this is over the normalizing thing, integral dw. And so, you know, we're still taking the derivative of this this exponential, but now it has a different form, right? So we have minus delta n log q by delta iw of r. And then again, because this arose because we were taking the derivative of something that's in an exponential, we still have the exponential term there. And so then that all goes back together to give us our Hamiltonian. Right? And so then this thing is what we're going to call our density operator. Right? So we'll call it rho tilde of r. So it's going to be spatially varying, and it's going to have a functional dependence on IW. And we're going to say that this thing is just going to be defined as minus n variation of log q over with respect to IW. And again, anybody with like a density functional theory type of background might recognize that you're basically just taking the derivative with respect to a chemical potential field, and that's going to give you a density. But it's kind of nice that we're able to sort of derive it this way. And the key property of this density operator is that when we take an ensemble average of rho of r, the thing that we've shown is that this is equal to the ensemble average of rho hat of r. It doesn't necessarily have to be true at the microstate level, but it does have to be true once we take an ensemble average, right? And so if we take an ensemble average of this operator, this minus n d log q diw, then that will give us something that's equal to the microscopic density after we've taken an ensemble average, right? And for the simple fluid case that we've been dealing with, we can write out, we know that q of IW is defined as 1 over v integral dr e to the minus IW of r. And so then evaluating this functional derivative is straightforward, and we end up with n over qv e to the minus IW of r in a simple, for this simple fluid density operator. All right, and again, just from my experience in working with field theories, this can be kind of a weird object. So for an instantaneous field configuration, this rho tilde, this density operator, can actually be imaginary. It can be locally imaginary. But once you take the ensemble average over field configurations, it had better go to being purely real. And that's kind of one way that you can assess the how well you've performed your averaging. All right, so I think this is the end of all the operator stuff. Let me see what I had next in my notes, because this might be a good stopping point for the day. Yeah, I guess just to summarize, to me, I think this is kind of a fantastic result, because if we just sort of summarize what we've done in total, right? We said that our partition function, from good old StatMech, we know that it's always this lambda t to the 3n dr to the n e to the minus u of r to the n. And to me, the cool thing that we have done is that without really making any approximations, we've shown that we can, we have a slightly different prefactor, but we can use an exactly equal sign and rewrite this as a field theory, right? And so we can do this particle to field transformation without using any approximations, at least not formally yet, and turn this into a field theory, which is now something that we will be able to attack analytically. And so that's what we'll start to work on over the next several lectures. Let me think. The next lecture is not until next Wednesday, and my plan for that one is to go over just a couple of example systems. We can use this framework provides a really elegant way of deriving like the Poisson-Boltzmann equation, So we'll talk about how to do a mean field approximation with the field theory. We'll go over a simple two-component system just to show where Flory-Huggins type things will come from. And we'll also apply it to a liquid crystal system with a Meyer-Sape interaction. Yeah, but if there are no final questions, then this will be about where we call it a day. All right, well. I was not seeing questions as they were coming up.
Can I ask a question?
Yeah, go for it.
Hi, thanks, Rob. So I have a question. So do you have an example or more intuitive way of understanding how there can be non-unique operators that give the same thing after averaging?
I can give examples of it. Are you asking like how to interpret that fact?
Yeah, or just how to get like a more intuitive grasp of how this ends up being possible. Because it still kind of blows my mind that this happens.
Yeah, it is. Yeah, it is a really weird thing. I mean, like let me see if I can put my equations back up. And are you a student in one of the field theory groups?
Postdoc and Glenn's groups.
Ah, cool.
Yeah.
Yeah, like the one where, I mean, I guess the other one that he emphasizes in the book is where you do the integration by parts at this step, right? And you end up with the U inverse times W of R is another operator that gives you the same thing. I sadly don't have a very strong intuition for it, and it's another weird case where like you can have these two operators that will give you different things instantaneously, but once you take the ensemble average, they average out to the same thing.
Yeah.
Yeah, I actually don't have a very clear intuition for why it works other than the math is sound.
Math, right? Okay, cool. Okay, glad to hear. Thanks again for the everything.
Yeah, no problem.